In June of 1905, a 26-year-old patent clerk published the most famous physics paper ever written, the one that shattered absolute time. But it does not open with time. It does not open with light, or speeding trains, or falling elevators. The first thing Albert Einstein wanted the world to look at was a magnet and a coil of wire. Because here is what the textbooks leave out. Magnetism, the force on your refrigerator door, the toy you played with as a child, has never been fully explained. Classical physics contains a rigorous proof that permanent magnets are impossible. Yours works anyway. Physics can predict a magnet's behavior to 12 decimal places and still cannot say what a magnetic field actually is. The magnetism of a simple copper wire turns out to be relativity itself, operating at the speed of a drifting snail. And the entire universe, planets, stars, galaxies, even the empty voids between them, is measurably magnetized, and nobody on Earth knows where the first magnetic field came from. Which leaves one question worth spending a night on. What is magnetism, really? Get comfortable. Hit subscribe if you're new here, because by the end of tonight, you will have the deepest answer physics can give, and it is far stranger than the question. Now, let's slowly ease into this. Part 1. The question in your hand. There is a gap between the two magnets you are holding, and something is happening inside it. You can feel it before you can name it. Push the two like poles toward each other, and your hands meet a resistance that has no surface, no texture, no temperature, a pressure exerted by nothing you can point to. Turn one magnet around, and the resistance becomes a pull, an insistence, as if the empty air between them had suddenly developed an opinion. Nothing is touching anything, and yet force is flowing through that gap, as surely as if you had tied the two together with rope. Most of us met this experience before we could read. A pair of toy magnets, a magnetic letter on a refrigerator door, the strange snap of two objects finding each other across a distance. And most of us, at some point, ask the obvious question: what is actually happening in that gap? What reaches across the space between the magnets? What is doing the pushing? Here is the uncomfortable truth that almost nobody says out loud. If you ask that question honestly, and you keep asking it every time an answer arrives, you will walk through the entire history of modern physics, and you will arrive, at the end of the walk, at a place where physics itself goes quiet. The question a 5-year-old asks about two toy magnets is, without exaggeration, one of the questions that created relativity, that demanded quantum mechanics, and that still, tonight, has an unsolved piece sitting at the center of cosmology. The answer exists in layers, and every layer is stranger than the one before it. By the end of tonight, we will have climbed all of them, and I will give you the real answer, the deepest one physics currently has, in plain language. But I am not going to give it to you now, because the answer only means something once you have felt the weight of the question. Let us start with what we can say for certain. Magnetism is not a curiosity. It is one face of one of the 4 fundamental forces of nature. Physics recognizes exactly 4 ways that anything in the universe can influence anything else. Gravity, which holds planets in orbit and pins you to your chair. The strong nuclear force, which binds the cores of atoms together. The weak nuclear force, which governs certain kinds of radioactive decay. And electromagnetism, which is responsible for essentially everything else you have ever experienced. Light is electromagnetism. Chemistry is electromagnetism. The firing of the neurons reading this sentence to you, the rigidity of the floor under your bed, the color of every object you have ever seen, the warmth of a fire, the signal carrying this voice to your ears, all of it is one force, the electromagnetic force, wearing different costumes. And here is a number worth sitting with. Between 2 protons, the electromagnetic force is stronger than gravity by a factor of roughly 10 to the power of 36. That is a 1, followed by 36 zeros. If gravity were a single drop of water, electromagnetism at the same scale would be an ocean many times larger than all the oceans on Earth. The comparison genuinely fails, because a number that large does not correspond to anything a human being has ever counted. The only reason the universe is not instantly torn apart by this force is that it comes in two signs, positive and negative, and matter is almost perfectly balanced between them. Every atom carries equal amounts of each, and so the ocean cancels itself, everywhere, to almost nothing. Gravity, absurdly feeble but relentlessly one-sided, is what remains to run the cosmos. Almost nothing, but not quite nothing. Because there are a few places where the cancellation slips, where the enormous hidden force leaks through into the world of hands and eyes. A spark of static electricity is one leak. Lightning is a bigger one. And the magnet in your hand is another. A place where the most powerful force in your everyday universe fails to fully hide, and you get to feel a diluted whisper of that 10 to the 36 directly against your fingers. That is what you are holding when you hold a magnet. Not a toy, a leak in the universe's most thorough cover-up. But knowing which force it belongs to is not the same as knowing what it is. And magnetism, even within its own family, is the strange sibling. Consider how oddly it behaves compared to the electricity it is supposedly related to. Electric force is straightforward in a way the mind accepts. Charges push and pull along the straight line between them, the way intuition expects a force to act. Magnetic force does no such thing. A magnetic field only exerts force on a charge that is moving, and when it does, it pushes sideways, always exactly at right angles to the direction the charge is traveling, not forward, not backward, sideways. A magnetic field can bend a particle's path into a circle, but it can never speed the particle up, and it can never slow it down. In the precise language of physics, a magnetic field does no work. It is a force that steers but never propels, redirects but never delivers energy, which should already strike you as odd, because you have watched a magnet lift a paperclip off a table, visibly fighting gravity and winning. Where the energy for that lift actually comes from is a subtlety that has generated debate in physics journals well into the 21st century. The most familiar force in your house has a footnote attached to its most basic behavior, and there is a deeper oddity, one we will spend much of tonight unwrapping. Electricity has particles. You can hold an isolated negative charge. Every electron is one. You can hold an isolated positive charge. Every proton is one. Magnetism, as far as every experiment in history can tell, has no particles of its own at all. There is no such thing as an isolated North Pole. Take the magnet in your hand and cut it in half, hoping to separate its north end from its south end, and you will not get a north piece and a south piece. You will get two smaller magnets, each with a complete north and south of its own. Cut again, and again, down to the level of single atoms, and the same thing keeps happening, forever. The poles are not parts of the magnet the way ends are parts of a rope. They are something else, something that cannot be isolated, cannot be extracted, cannot be bottled. Magnetism is a force that appears to have no substance that carries it. So let me lay the full question on the table, the one this entire night is built to answer. When you feel that push between two magnets, when force crosses a gap where nothing is touching anything, what is in the gap? Is it a thing, a physical entity filling the space, as real as the magnets themselves? Is it a kind of accounting trick, a shadow cast by something else? The men and women who chased this question were not fools, and they were not minor figures. The chase runs through a Danish lecture hall in the spring of 1820, through a bookbinder's apprentice who saw pictures where others saw equations, through a Scottish mathematician who accidentally discovered what light is, and through a 26-year-old patent clerk in Bern who noticed that the standard explanation of a magnet and a coil of wire contained a contradiction so troubling that fixing it required rewriting the nature of time. Every one of them peeled back a layer. None of them reached the bottom. And the strangest part, the part I will show you as we go, is that the force you are picturing right now, the horseshoe magnet, the fridge door, the compass needle, turns out to be woven into everything at every scale. It is in the wire in your wall. It is in the spin of particles that are not, in any ordinary sense, spinning. It is wrapped around this planet like a shield, wound through our galaxy like thread through fabric, and stretched, measurably, unmistakably, across the emptiest voids in the observable universe, where by every classical argument it has no business existing at all. Something with no substance, that pushes without touching, that steers without giving energy, that has no isolated charge, and that fills the universe from your kitchen to the gaps between galaxy clusters. That is the thing we are going to spend tonight trying to understand. And the honest place to begin is with a confession on behalf of our species. For the first 2,000 years we knew about this force, we did not understand it at all, and we used it to conquer the world anyway. Part 2. 2,000 Years of Pointing. Somewhere in the ancient world, more than 2,000 years ago, a person picked up a stone that behaved wrongly. It was a dark, heavy, unremarkable-looking mineral, the kind of stone you would step over without a glance, except that it grabbed iron. Small pieces of iron leapt to it and clung. Iron tools brushed against it came away changed, briefly able to attract other iron themselves, as if the stone had breathed something into them. The Greeks knew this stone, the Chinese knew it. It occurs naturally all over the world, a mineral we now call magnetite, an oxide of iron with the chemical formula of 3 iron atoms bound to 4 oxygen atoms, that sometimes emerges from the ground already magnetized, most likely by the enormous currents of lightning strikes. The traditional story, passed down through Roman writers, is that the very word magnet comes from Magnesia, a region of ancient Anatolia in modern-day Turkey, associated with deposits of the ore. Whether or not the etymology is true, the point stands. Human beings have been holding magnetism in their hands and wondering about it since before the alphabet reached its modern form. The ancient explanations are worth pausing on, because they are not stupid. They are the honest first attempts of minds meeting something that violates the deepest rule of intuition, the rule that says influence requires contact. The Greek philosopher Thales, according to later writers, suggested the lodestone had a soul because it could cause motion, and causing motion was what souls did. Roman poets imagined invisible hooks and streams of particles. Chinese natural philosophy folded the stone's behavior into the great system of sympathies and correspondences that organized their cosmos. Every one of these is a way of saying the same thing. Something crosses the gap, and we cannot see what it is. 20 centuries later, that sentence has survived every revolution in physics, essentially intact. The explanations improved beyond recognition. The gap remained. What happened next is one of the great ironies in the history of knowledge. Humanity took this force it could not explain and used it to redraw the map of the world. At some point, the earliest clear descriptions come from China. Someone discovered that a piece of lodestone, or an iron needle stroked against one, would do something no other object in the world would do. It would choose a direction. Han Dynasty texts, from around 2,000 years ago, describe lodestone spoons that swiveled on polished boards, used not for travel, but for divination and the alignment of buildings. The decisive step arrives by the 11th century, in the writings of the Song Dynasty scholar Shen Kuo, who described a needle, magnetized by lodestone and suspended by a silk thread, that would settle itself along the north-south line. He even recorded, with an accuracy that still impresses geophysicists, that the needle did not point at true north exactly, but slightly aside of it, a phenomenon we now call magnetic declination. Europe's first written mention of the compass comes more than a century later, around the year 1190. Think about what the compass actually is, as a physical object. It is a detector of an invisible planetary force field, built by people who had no concept that such a thing existed. A sliver of magnetized iron, floated on water or balanced on a pin, so sensitive that it could respond to a field roughly 20 times weaker than the pull of a cheap refrigerator magnet. And it worked everywhere. In fog, at night, under clouded stars, in the middle of an ocean with no landmark, for 1,000 miles in any direction, the needle quietly held its line. The age of global navigation, the crossings of oceans, the linking of continents, the entire redrawing of human civilization between the 12th and 17th centuries, ran on an instrument whose operating principle not one person aboard any of those ships could have explained. Not the captain, not the instrument maker, not the greatest scholar in the greatest university of the age. Nobody on Earth knew why the needle pointed. Pointing, it turns out, is not understanding. And for 500 years of ocean crossings, pointing was enough. The needle's secret finally began to crack in 1600, and the way it cracked matters as much as the answer. William Gilbert was a physician, personal doctor to Queen Elizabeth I of England, and in his spare hours, over nearly 2 decades, he did something that was at the time genuinely radical. Instead of reasoning about the lodestone from ancient texts, he experimented on it. Systematically, obsessively, he had spheres carved out of lodestone, little globes of magnetic rock he called terrellas, little earths, and he moved compass needles across their surfaces, degree by degree, mapping how the needle tilted and turned. And he noticed the needle behaved on his stone sphere exactly the way ships' compasses behaved on the surface of the real planet. Near the sphere's equator, the needle lay flat. Near the poles, it dipped nose down toward the stone, just as sailors' needles were known to dip more steeply at high latitudes. In his book De Magnete, published that year, Gilbert drew the conclusion that no one in 20 centuries had dared to put in writing. The reason a compass points is that the Earth itself is a magnet. The needle was never pointing at the heavens, at the pole star, at anything celestial. It was answering the planet under the sailor's feet, a sphere of rock 8,000 miles across, holding an invisible grip on every scrap of magnetized iron on its surface. De Magnete is sometimes called the first great work of experimental science, published 9 years before Galileo raised a telescope, and Gilbert added a second gift, almost in passing, that would take on enormous weight later. He carefully studied the other famous attraction of the ancient world, the way-rubbed amber pools in chaff and dust, and showed it was a different phenomenon from magnetism, following different rules. He coined a new Latin word for the amber effect, from the Greek word for amber, electron. He called it electricus. The word electricity enters the human story here, in a book about magnets, introduced specifically to say that electricity and magnetism are not the same thing. Hold that thought, because the next 2 centuries of physics organized themselves around Gilbert's separation. 2 forces, 2 sciences, 2 shelves in the library, and the moment that wall fell is the moment the modern world begins. But before we knock the wall down, sit for a moment with how the situation stood, because it is stranger than we usually admit. By the year 1800, humanity had crossed every ocean on Earth behind a magnetized needle. Gilbert had shown the planet itself was the magnet the needles obeyed. And yet if you had asked the finest mind in Europe the child's question, what actually reaches across the gap between the Earth and the needle, what is in the space between a lodestone and a nail, you would have received, in essence, the same answer Thales gave, a shrug dressed in better vocabulary. Some spoke of subtle fluids flowing through iron. Some spoke of effluvia, invisible streams. The mathematics of attraction had improved. The understanding of it had not moved. 2,000 years of use. 2,000 years of empires and voyages and fortunes built on this force. And the sum total of human insight into what it actually was amounted to almost exactly nothing. There was even a warning sign, recorded and ignored, that the needle's master was not as steady as a planet ought to be. Navigators, keeping careful logs across the 1600s, noticed that the declination Shen Kuo had described, the small angle between magnetic north and true north, was not fixed. It drifted. Year by year, decade by decade, the direction of magnetic north crept across the sky of the compass card, which meant the great magnet inside the Earth was moving, changing, alive in some way that solid rock should not be. Gilbert himself had noticed something equally suggestive in his workshop. Heat a magnetized piece of iron until it glowed, and its magnetism simply died. Whatever this force was, it could be killed by fire, and it wandered on its own schedule. A permanent force that was not permanent, radiating from a planet that behaved like a machine with moving parts. Both clues pointed at truths that would take another 3 centuries to unfold, and we will meet both of them again before this night is over. What nobody suspected, what nobody could have suspected, was that the answer had been lying in plain sight the whole time, on the other shelf of the library. The key to the lodestone was not hidden in the lodestone. It was hidden in Gilbert's other force, the amber force, the one he had so carefully fenced off with its own new name. Electricity and magnetism, separated at birth in 1600, were about to collide in a lecture hall in Copenhagen, by accident, in front of an audience, in the spring of 1820, and the collision would be witnessed by a compass needle doing something no compass needle was supposed to do. Part 3. The wire that moved a needle. The wall between electricity and magnetism stood for 220 years, and it fell in the middle of a physics lecture. In April of 1820, at the University of Copenhagen, a Danish professor named Hans Christian Ørsted was demonstrating the passage of electric current through a wire, a fashionable topic since the battery had been invented by Alessandro Volta only 20 years earlier, and electricity was, for the first time in history, something you could switch on and off at will, rather than wait for in a thundercloud. On the lecture table, near the wire, sat a compass. Accounts differ on whether its placement was deliberate or incidental, and Ørsted himself later suggested he had long suspected a connection. What is not in dispute is what happened. When the current flowed, the compass needle moved. It did not leap. Witnesses described the effect as small, almost unimpressive, a twitch, a modest swing. But consider what that twitch meant. A compass needle answers to magnets. That is the entirety of its job description. There was no magnet on the table. There was only a wire carrying electric current. Gilbert's other force, the amber force, the one fenced off in its own separate science for 2 centuries. And the needle answered it. Electricity, flowing, had reached across the gap and touched the one instrument in the world designed to detect magnetism. The wall was not just cracked. In one quiet motion of a sliver of iron, it was revealed to have been an illusion all along. Ørsted did what a careful scientist should do. He spent 3 months repeating and varying the experiment before saying a word in public. He tried thicker wires and thinner ones, stronger currents and weaker, needle above the wire and needle below, and buried in his measurements was a detail so strange it deserves more attention than it usually gets. The needle did not point at the wire, the way iron points at a lodestone. It did not point along the wire either. It settled sideways, crosswise to the current, as if the influence flowing out of the wire were not radiating outward like heat from a flame, but circulating around the wire, wrapping it in closed rings. Magnetism did not point at its source. It curled around its source. Nothing in 2,000 years of natural philosophy had prepared anyone for a force shaped like that. In July of 1820, Ørsted published his findings in a 4-page pamphlet, written in Latin so every scholar in Europe could read it. The pamphlet crossed the continent in weeks, and everywhere it landed, laboratories caught fire with activity. Nowhere did it land harder than Paris. News of the Danish experiment was presented to the French Academy of Sciences at the start of September 1820. In the audience sat André-Marie Ampère, a professor of mathematics whose life had been scarred twice, first by the execution of his father during the Revolution, then by the early death of his wife, and who had poured himself into science with the intensity of a man who needed somewhere to put his mind. 1 week later, Ampère stood before the Academy with his own results, and they went beyond Ørsted's in a decisive way. If a current creates magnetism, Ampère reasoned, then 2 currents should behave like 2 magnets. They should act on each other. He ran current through 2 parallel wires, with no iron anywhere in the experiment, and watched them move. Currents flowing in the same direction, the wires drew together. Opposite directions, they pushed apart. 2 pieces of plain copper, attracting and repelling each other across empty air, with not a scrap of lodestone in sight. Stop and feel the weight of that result, because it quietly inverts the entire ancient question. For 20 centuries, magnetism meant special stones, a rare property of a rare mineral. Ampère's wires said no. Magnetism is not a property of stones. Magnetism is what moving electric charge does. Any moving charge, anywhere. The lodestone was never the phenomenon. It was one obscure example of the phenomenon, and the real headline is that electricity in motion wraps itself in the same invisible grip that turns compass needles. Ampère pushed the logic to its natural conclusion with a proposal of extraordinary nerve for 1820. Perhaps there are no magnetic substances at all. Perhaps the lodestone itself, the iron needle itself, are full of tiny circulating electric currents, loops of charge too small to see, all orbiting in alignment, adding their little magnetisms together into the pull you feel. He could not prove it. The atom itself was still a philosophical guess. But hold his idea in your mind tonight, because when we finally descend into the interior of a magnet, near the end of our journey, we are going to find something astonishingly close to what Ampère imagined, with one quantum twist he could never have foreseen. The third figure in this decade of collapse worked in London, and he came from nowhere. Michael Faraday was the son of a blacksmith, apprenticed at 14 to a bookbinder, a man with no university, no mathematics, and no social standing in the gentleman's world of English science. He educated himself by reading the books he bound. He talked his way into a job as a laboratory assistant at the Royal Institution, and rose, through 2 decades of the finest experimental hands in Europe, to become the greatest experimentalist who has ever lived. In 1821, following up on Ørsted and Ampère, he built a device in which a current-carrying wire circled endlessly around a magnet, the first electric motor in history, a toy that would remake civilization within a century. But his masterpiece came 10 years later. Ørsted had shown electricity creates magnetism. For a decade, Faraday kept returning to the mirror question: can magnetism create electricity? Can the influence run backward? In August of 1831, he found the answer, and it carried a condition nobody expected. Faraday wound 2 separate coils of wire around an iron ring, coils connected to each other by nothing except the iron they shared. When he drove current through the first coil, a needle attached to the second coil twitched, and then went still, even though the current in the first coil kept flowing. When he cut the current, the needle twitched again, in the opposite direction. Steady magnetism, he realized, creates nothing. It is change that creates. Move a magnet into a coil of wire, and current flows. Hold it still, and the current dies. Pull it out, and the current flows the other way. The universe, it turns out, pays out electricity only when magnetism is changing, a rule now called electromagnetic induction. If that sounds like a laboratory footnote, look around the room you are lying in tonight. Essentially every watt of electric power on this planet, from coal plants, gas plants, nuclear stations, hydroelectric dams, wind turbines, is generated one way, by rotating a magnet near a coil of wire. Faraday's 1831 experiment, scaled up and spun by steam and falling water, is the beating heart of the electrified world. When the lights in your home are on, they are on because somewhere a magnet is moving. The practical world did not wait for understanding, any more than the navigators had. Within 5 years of Oersted's pamphlet, the English inventor William Sturgeon wrapped bare wire around a varnished iron bar and produced the first electromagnet, a magnet you could switch on and off with a battery, something no lodestone in 20 centuries had ever offered. Within another decade, improved electromagnets were lifting hundreds of times their own weight, and clicking armatures at the far ends of long wires were spelling out messages. The telegraph, the first machine to move information faster than a horse, built directly on the marriage of the two forces. Humanity's oldest pattern was repeating itself in fast forward. Use first, understanding later, the compass all over again, except this time the world was being rewired in a single generation. In one decade, 1820 to 1831, the two forces Gilbert had separated collapsed into a single tangle. Electricity in motion makes magnetism. Magnetism in change makes electricity. Each conjures the other, back and forth, a pairing too intimate to be a coincidence. And yet notice what had actually been answered. The child's question from the beginning of tonight, what is in the gap, what crosses the space, had not been touched. If anything, it had grown sharper, because now the mystery had multiplied. Whatever surrounds a magnet also surrounds a humming wire, wraps it in circles, and reaches across space to grab other wires. The laws connecting the forces were falling into place, one experiment at a time. The thing itself, the presence in the gap, remained as invisible and unnamed as it had been for Thales. It was Faraday, the man without mathematics, who finally gave it a name, and the name he chose, and the picture in his head when he chose it, would become the single deepest idea in all of physics. Part 4. The Invention of the Field. Michael Faraday could not read the mathematics of his contemporaries, and it may be the luckiest limitation in the history of science. Where the mathematicians of Paris described electricity and magnetism as forces acting directly across empty distance, clean equations connecting charge to charge, with nothing at all in between, Faraday, the picture thinker, could not accept the emptiness. He had spent too many hours watching iron filings. Scatter filings on a sheet of paper, hold a magnet beneath, tap the sheet gently, and the filings organize. They chain themselves into arcs, sweeping in nested curves from one pole of the magnet to the other, a pattern as orderly as the grain of wood. You have probably seen it. Faraday saw it thousands of times, and he became convinced the filings were not creating the pattern. They were revealing it. The curves were already there, in the space itself, before a single filing landed. Invisible lines of influence, filling the gap around every magnet and every current-carrying wire, real as rope. He called them lines of force, and the region they filled came to be called the field. Try to feel how radical this is. Faraday was proposing that what we call empty space around a magnet is not empty. It is occupied, structured, organized, under tension, by something with no weight you can put on a scale and no surface you can touch. The magnet, in this picture, does not reach across nothing to grab a nail. The magnet fills the space around itself with a field, and the field grabs the nail. The gap between your two magnets from the beginning of tonight is not a gap at all. It is a medium, an invisible architecture. And the push you feel in your hands is that architecture pressing back. So stand inside it for a moment, shrink yourself down, in imagination, and float in the space between the two poles of a horseshoe magnet, the gap where, tonight's opening insisted, nothing is touching anything. Around you, the darkness is threaded. Smooth arcs sweep past you from one pole toward the other, dense and crowded directly between the poles, spreading and thinning as they bow outward into the room. Along the direction of the lines there is tension. Each line pulls taut, like a stretched elastic cord, straining to shorten itself. Across the lines there is pressure. They shoulder against each other, refusing to be crowded, spreading themselves as evenly as the geometry allows. Reach out and drag your hand across the pattern, and you feel resistance, a springiness stored in nothing visible at all. This tension along the lines is the pull that snaps two unlike poles together. This sideways pressure between crowded lines is the push that shoves two like poles apart. Every behavior of the magnets in your hands is the mechanics of this hidden structure. And when a stray iron filing tumbles into the space, you watch it swing obediently into line with the arcs around you, a compass needle, at the bottom of an invisible sea that was here all along. The gentlemen of mathematical physics were, for the most part, unimpressed. Lines of force in empty space sounded like the doodle of a laboratory hand who had never mastered calculus, a crutch for a mind that could not handle proper equations. It took a mathematician of the first rank to see what Faraday's pictures really were. James Clerk Maxwell, a Scot educated at Cambridge, began corresponding with the aging Faraday in the 1850s, and where others saw doodles, Maxwell saw geometry begging for formalization. Over roughly a decade, he translated lines of force into exact mathematics, and in 1865 he published the result in the Philosophical Transactions of the Royal Society, under the title A Dynamical Theory of the Electromagnetic Field. The word field is right there in the title, promoted from laboratory picture to the central object of a physical theory. Everything electricity and magnetism had ever been observed to do, Oersted's needle, Ampere's wires, Faraday's induction, Gilbert's planet, the lodestone of magnesia, fell out of one compact system of equations describing how electric and magnetic fields are generated, how they spread through space, and how each responds to changes in the other. In its original form, the theory sprawled across 20 equations. It was later condensed into the 4 that physics students now learn as Maxwell's equations. And it is worth knowing that the compact modern form is largely the work of Oliver Heaviside, a self-taught former telegraph operator, unemployed and living with his parents, who reshaped the masterpiece in 1884. This subject has a habit of being advanced by outsiders, the bookbinder, the telegrapher. It is worth pausing on what a field actually is, in the mathematics, because the definition is at once perfectly precise and strangely hollow. A field is an assignment of a quantity to every point in space. Pick any location in the room around you, a spot above your left shoulder, a point inside your pillow, a position halfway to the ceiling, and the magnetic field has a definite value there, a strength and a direction, this many microteslas, pointing that way. Move a millimeter and it has another value. The field is the complete set of these values, everywhere, at every instant, space itself treated as a thing with properties at every point, rather than as the absence of things. Physics has never found a deeper way to say what a field is than that. It is defined entirely by what it does at each location, never by what it is made of. Keep that hollowness in mind. It is not a temporary gap awaiting a better textbook. It is, a century and a half later, still the honest bottom of the explanation. And buried in Maxwell's equations was a surprise that nobody, including Maxwell, had gone looking for. The equations permitted something strange, a travelling knot of electric and magnetic fields, sustaining itself in empty space, with no charges and no magnets anywhere nearby. A changing electric field, Maxwell's mathematics said, generates a magnetic field. A changing magnetic field generates an electric field. Set both changing together, in just the right embrace, and each continuously midwives the other into existence. A wave of pure field, rolling through the void, feeding on nothing but its own rhythm. The equations even specified this wave's speed, computable from two constants measured on laboratory benches with batteries, coils, and jars. Numbers describing the strength of static electric attraction and of magnetic forces between currents, with no reference to light or motion whatsoever. Maxwell put the constants in and turned the crank. Out came a number, roughly 300,000 kilometers per second. The speed of light, measured by astronomers, known with growing precision for 2 centuries, and never once suspected of having anything to do with magnets. Maxwell wrote, with a restraint that reads today like a whisper before a thunderclap, that it seemed he could scarcely avoid the inference, light itself is an electromagnetic wave. Sit with what was just discovered, in a paper about fields. Light, sunlight, firelight, starlight, the entire visible universe, every color your eyes have ever registered, is electric and magnetic fields regenerating each other in flight. The pattern of arcs you just floated inside, between the poles of a horseshoe magnet, is made of the same stuff as a sunset. Your eyes are field detectors. When you look at anything at all, you are performing an act of magnetism. Faraday's filing patterns, and the light by which he observed them, were one phenomenon at 2 tempos, and nobody in human history had noticed. Physicist Freeman Dyson would later call Maxwell's paper the most important event of the 19th century in the history of the physical sciences, ranking it, in consequence, above every war and every empire of that 100 years. The judgment sounds extravagant until you inventory the 20th century's machinery. Radio, television, radar, X-rays, microwaves, fiber optics, the wireless signal carrying this voice into your room right now. All of it lives inside that 1865 paper. But here is the question I want to leave hanging in the dark with you, because the whole night turns on it. Maxwell answered what is in the gap with the field, and the field passed every test. It carries energy, measurably, undeniably. The warmth of the sun on your face is field-borne energy that crossed 150 million kilometers of vacuum to reach your skin. It carries momentum. Light exerts a real, measurable pressure on whatever it strikes. It can detach from its sources entirely and travel forever. The starlight arriving at your window tonight left its stars before you were born, and the stars could die without recalling it. Energy, momentum, independence. The field has every credential of a physical thing. And yet, what is it? What is doing the waving in an electromagnetic wave? What substance holds the tension in Faraday's lines? The 19th century had a ready answer. A universe-filling material called the luminiferous ether, the stuff whose ripples light was assumed to be. Every attempt to detect that material failed. And the failure was about to be examined by a 26-year-old examiner of patent applications in Bern, Switzerland. A man who had noticed that Maxwell's magnificent theory contained, right at its center, a small and infuriating asymmetry involving nothing more exotic than a magnet and a loop of wire. Part 5. The asymmetry that bothered Einstein. The most famous physics paper ever written was published in June of 1905 by an author with no university position, no laboratory, and no academic standing whatsoever. A 26-year-old technical expert, third class, at the Swiss Federal Patent Office in Bern, who did his physics in the evenings and, by most accounts, at his desk between patent applications. The paper is the one that gave the world special relativity, the theory that moving clocks run slow, that moving objects contract along their direction of travel, that simultaneity itself depends on the observer, the theory that dismantled absolute time. Everyone knows what the paper did. Far fewer people know how it opens. It does not open with time. It does not open with light, or with trains, or with any of the famous imagery attached to it since. The title is On the Electrodynamics of Moving Bodies, and the first paragraph, the very first thing Albert Einstein wanted the reader to think about, is a magnet and a coil of wire. That choice should stop you. The paper that rewrote the nature of time begins with the same subject we have been following all night, and that is not a coincidence or a stylistic flourish. It is the whole point. Special relativity was not born from thinking about time. It was born from thinking about magnetism, from one small, stubborn ugliness in Maxwell's otherwise perfect theory that apparently nobody else found as intolerable as the patent clerk did. Here is the asymmetry, exactly as Einstein laid it out, and it requires nothing beyond what we have already learned tonight. Take a magnet and a loop of conducting wire. Faraday taught us what happens when they move relative to each other. Current flows in the loop. Now perform the experiment two ways. First way, hold the loop still and move the magnet toward it. Second way, hold the magnet still and move the loop toward it at the same speed. Do the measurement. In both cases, the result is identical. The same current, the same deflection of the meter, down to the last decimal place. Nature plainly does not care which object moved. Only the relative motion, magnet toward loop, appears anywhere in the outcome. But now ask the theory, Maxwell's theory, the crown jewel of 19th century physics, to explain the two cases, and something embarrassing happens. The theory tells two completely different stories. In the first case, it says, the magnet is moving, so the magnetic field at each point of space is changing, and a changing magnetic field creates an electric field. That is Faraday's induction, written into Maxwell's equations, and this new electric field grips the charges in the stationary loop and drives them around the circuit. An electric field exists, and it does the pushing. In the second case, the theory says, the magnet is at rest, its field is static and unchanging, and therefore no electric field exists anywhere. Instead, the charges inside the moving loop are being carried through a magnetic field, and a magnetic field pushes on moving charges, so the magnetic force drives them around the circuit. Same current, same meter reading, but in one story, an electric field fills the room and does all the work, and in the other story, that electric field simply does not exist, and a magnetic force does everything instead. The theory's two explanations disagree about what is real in the room. Is there an electric field present, or is there not? Maxwell's equations answer, it depends on which object you decided to call the moving one. And that decision, this is the part that gnawed at Einstein, corresponds to nothing physical. The current does not know which story produced it. The experiment cannot tell the difference. As Einstein put it in that opening paragraph, the observable phenomenon depends only on the relative motion of the conductor and the magnet, whereas the customary view draws a sharp distinction between the two cases. The distinction is in the theory, not in the world. The universe, evidently, does not come with labels reading this part electric, this part magnetic. The labels were coming from somewhere else. They were coming from us, from the choice of who is said to be moving. Most physicists of the era knew about this wrinkle and shrugged. The equations gave the right answer in both cases. Why lose sleep over the bookkeeping? It takes a particular kind of mind to look at a theory that predicts every experiment correctly and still insist that it must be wrong about reality because its explanations are not symmetric. There is a story about Einstein, one he told himself, late in life, that as a child of 4 or 5, sick in bed, his father brought him a pocket compass, and the sight of the needle swinging to its invisible master shook him so deeply that he described the memory decades later as the moment he understood that something deeply hidden had to be behind things. Whether or not memory embellished the moment, The pattern is hard to miss. The child unsettled by the compass needle became the man unsettled by the magnet and the coil, and both times the instinct was the same. The visible behavior is fine. It is the hidden explanation that smells wrong. And there was a second failure in the air, feeding the same suspicion. Maxwell's waves needed a medium, the luminiferous ether, the substance whose undulations light was supposed to be, filling all of space like an invisible ocean. If the ether existed, the Earth had to be ploughing through it as it orbits the Sun at 30 kilometers every second, and a laboratory on Earth should be able to detect the resulting ether wind as a difference in the speed of light along different directions. In 1887, in Cleveland, Ohio, Albert Michelson and Edward Morley built an apparatus of exquisite sensitivity. Light beams racing along two perpendicular arms floated on a slab of stone in a pool of mercury, specifically to measure that difference. They found nothing. No wind, no difference, no trace of the medium in the most sensitive optical experiment ever performed to that date. The field's supposed substance refused to appear, and the two explanations of the magnet and the coil refused to agree. And both refusals pointed a finger at the same unexamined assumption, an assumption so basic it had never been stated as an assumption at all. It is worth remembering what year this was for the man at the patent desk. 1905 is remembered in physics as the miracle year. In a span of months, alongside his day job, Einstein published a paper explaining the photoelectric effect by proposing that light comes in discrete packets, the paper that would seed quantum theory and win him the Nobel Prize, a paper on Brownian motion that effectively proved atoms exist, the relativity paper, and a short follow-up containing the most famous equation ever written, connecting energy to mass. 4 detonations in one calendar year, and the relativity paper, the deepest of them, grew directly out of the humblest apparatus on our night's table, a magnet, a coil, and an explanation that told 2 stories where nature told one. Einstein's move, in June of 1905, was to take the experiment's verdict with total seriousness and demote everything else. If nature says only relative motion matters, then only relative motion is real. There is no absolute rest, no ether ocean, no privileged standpoint from which the universe's true labels can be read. And if every observer, moving or not, always measures light at the same speed, as Maxwell's equations and every experiment insisted, then something else must give. What gives, Einstein showed, is time and space themselves. 2 observers in relative motion genuinely disagree about the length of a meter stick and the tick of a second, and both are right, because there was never a master clock or a master ruler to be right about. This is the theory the magnet and the coil demanded. Notice what it immediately does to our subject. If observers in relative motion disagree about space and time, and electric and magnetic fields are defined across space and time, then the 2 observers watching that magnet and coil are not telling contradictory stories about one reality. They are correctly describing what each of them actually finds. One of them living in a room with an electric field in it, the other in a room with none. The way 2 people viewing a statue from different angles truthfully report different silhouettes. The electric and the magnetic are not 2 substances. They are 2 projections of a single thing, and the split between them is chosen by your motion. Which brings us to a promise. If motion is what carves the one field into electric and magnetic parts, we should be able to catch the carving in the act, to take an ordinary electric situation, view it from a sliding vantage point, and watch magnetism appear out of nothing. Not as a metaphor, as an audited calculation, with real numbers from real copper. That calculation exists. It concerns the most ordinary object imaginable, a current-carrying wire, the kind buried in the wall behind your headboard, and it is, for my money, the single most astonishing arithmetic in all of physics. It is where we go next. Part 6. Magnetism is relativity you can hold. Begin with the wire, an ordinary copper wire carrying an ordinary direct current, the kind of situation that exists in millions of places within a kilometer of wherever you are lying right now. Inside the copper, there are two populations of charge. There is the lattice, copper atoms stripped of one electron each, positive ions locked in a crystal grid, going nowhere. And there is the sea, the liberated conduction electrons, negatively charged, drifting along the wire under the gentle pressure of the battery. In every section of the wire, the positive charge of the lattice and the negative charge of the drifting sea balance exactly. The wire is electrically neutral. Bring a charged particle near it and hold it still, and the particle feels nothing at all, no attraction, no repulsion. The mountain of electric force is perfectly cancelled. Now ask how fast the electron sea is actually drifting, because the answer is one of the great secrets of the everyday world. When you flip a light switch, the lamp responds instantly, so intuition says the electrons must race down the wire near the speed of light. They do not. What races is the field, the influence, the electromagnetic wave guided along the outside of the wire. The electrons themselves creep. In a typical household copper wire carrying a typical current, the drift speed of the conduction electrons is on the order of 1/10 of 1 millimeter per second. Let me translate that. A garden snail sprints several times faster. An electron, drifting through the cord of your bedside lamp, would need roughly 3 hours to travel 1 meter. The current powering your home is, at the level of the particles, slower than the minute hand of a clock is at its tip. Hold on to that almost comical slowness, because we are about to feed it into the most delicate scale in the universe. Set a single positive charge outside the wire, and this time let it move, gliding parallel to the wire, in the same direction the electron sea drifts. Laboratory instruments report what happens next, without ambiguity. The moving charge curves toward the wire. 19th century physics has a ready name for this. The wire's current wraps it in Ørsted's circular magnetic field. The charge is moving through that field. Moving charges in magnetic fields feel a sideways push. Magnetic force. Case closed. But now do what Einstein taught us to do. Climb aboard. Shrink down and ride alongside that positive charge, matching its glide exactly, so that in your frame of reference, the charge sits dead still beside you. And here the trap springs shut. A magnetic field can only push on a moving charge. That has been its defining behavior all night. Your charge is not moving. Whatever magnetic field may or may not surround you, it is powerless to touch a stationary charge. Its force on it is precisely zero. Yet the curving is still happening. It must be, because a deflection is an event, and observers cannot disagree about events. If the charge strikes the wire in one frame of reference, it strikes the wire in all of them. Something in your frame must be pushing it, and it cannot be magnetism. Look at the wire from your new seat, and look closely, because the resolution is hiding in the geometry of the two charge populations. From where you now glide, the drifting electron sea is the population at rest. You are moving along with it, so the electrons hang beside you, nearly motionless. But the positive lattice, stationary in the old frame, now streams backward past you. And special relativity says something exact about things that stream past you. They contract along their direction of motion. The moving lattice squeezes, ever so slightly, and its positive ions pack closer together than before, more positive charge per centimeter of wire. Meanwhile, the electron sea, which was contracted in the laboratory frame where it was the moving population, relaxes in yours. Its negative charge spreads thinner. Count the charges again. The balance is broken. Per centimeter of wire, one sign of charge now outnumbers the other. The wire, scrupulously neutral in the laboratory frame, is, in your frame, an electrically charged rod, and a plain, honest electric force acts on the charge resting beside you. Run the arithmetic with full care, tracking every sign, and the electric push in your frame comes out identical, in strength and in direction, to the magnetic push the laboratory frame reported. The two frames agree on the event, as they must. They simply file it under different names. The deflection every observer witnesses is called magnetic, by the observer watching the wire, and electric, by the observer riding the charge. Same event, two ledgers, both correct. And neither ledger is the true one, because there was never a true frame to keep it in. Now for the arithmetic that should not work. The relativistic effects we just invoked are supposed to be imperceptible at low speeds, and 1/10 of a millimeter per second is the definition of a low speed. Run the numbers, and the length contraction of the ion lattice at drift velocity alters lengths by roughly 1 part in 10 to the power of 26. 1 part in 100 million billion billion. No instrument on Earth could measure that contraction directly. It is trillions of times too small for the finest interferometer ever built. By any sane intuition, an effect that small is zero. It is nothing. And yet, here is the number on the other side of the scale. A single centimeter of copper wire contains roughly 10 to the power of 23 charges of each sign, and the electric force between charges is titanic beyond metaphor, 10 to the power of 36 times stronger than gravity. What the frame change does is take an imbalance of 1 part in 10 to the 26 and hand it to a force of magnitude 10 to the 36, acting among 10 to the 23 particles per centimeter. Multiply the absurdly small by the absurdly enormous, and out comes a force of ordinary, human workshop size. The force that spins a drill, slams a relay, drives a subway train out of its station. Magnetism is what happens when the most powerful force in the universe fails to cancel by 1 part in 100 million billion billion. Because someone is watching from a moving seat. Let the realization land all the way. Every electric motor you have ever heard hum, the refrigerator compressor cycling in your kitchen right now, the fan turning somewhere in your home tonight, the wheels of every electric train and car on this planet, is running on special relativity, the theory of warped time and contracted space, the theory that is supposed to live near the speed of light and in the neighborhoods of black holes, is operating in your house at 1/10 of a millimeter per second, disguised under the old Greek name of a stone from Magnesia. You were told relativity was exotic. It is the reason a doorbell works. Faraday and Ørsted were handling relativistic physics with their bare hands 80 years before Einstein was born. The effect was simply wearing a mask, and the mask had been named magnetism 20 centuries earlier. When Einstein was later asked about his discovery of relativity, he said that the magnet and conductor problem led him to it. The answer to what is in the gap between your two magnets has become the same thing that is in an electric field, viewed by an observer whose motion rebooks the universe's accounts. There is a quieter version of this realization, and it may reach deeper than the motors and the trains. If magnetism is the relativistic shadow of electricity, then the speaker, or the earbud delivering this sentence to you, is performing the trick at this exact moment. A coil of wire, a magnet, and a membrane, with the coil's current rebooked frame by frame into forces that push the membrane back and forth hundreds or thousands of times per second. Every word you have heard tonight has been carried to you across that 1 part in 10 to the 26 imbalance. The sound of this voice is, in a completely literal sense, the sound of special relativity at work, and it has been the sound of every voice you have ever heard through any speaker in your life. Nobody mentions this. It is simply how the world has hummed along, all around you, since before you were born. And yet, hold your two magnets again, because something does not fit, and I promised you at the start of tonight that I would not hand you a tidy answer with the loose thread tucked out of sight. The wire story explains the magnetism of currents, charges visibly flowing, but the magnet on your refrigerator has no battery, no circuit, no current you can point to. It has been holding the same grip without an energy source for years. And if it is a lump of frozen relativistic bookkeeping, then what exactly is moving inside it, and why does it never stop? When physicists of the early 20th century tried to answer that with the classical physics we have assembled so far, Maxwell's fields plus ordinary matter, they got a result so devastating that it remains one of the least told stories in science. They proved, with complete rigor, that permanent magnets are impossible. The magnet on your refrigerator violates classical physics. Not approximately, absolutely. That proof, and the escape from it, is where we go next. Part 7. The Theorem that Forbids Magnets. Let us step back for a moment and stack up what we have built, because we have come a long way from the toy magnets, and the next turn in the road only lands if you can feel the whole structure under your feet. We began with a child's question: what is in the gap between two magnets, where nothing is touching anything? We learned that the force in that gap belongs to electromagnetism, one of the four fundamental interactions, a force 10 to the power of 36 times stronger than gravity that hides itself through almost perfect cancellation. We watched humanity use the force for 2,000 years without understanding it. Pointing is not understanding. Until a compass needle twitched beside a wire in Copenhagen in 1820, and a single decade collapsed electricity and magnetism into one tangle. We met Faraday's answer to the gap, the field, an invisible structure filling space, made respectable by Maxwell's mathematics, and crowned by the discovery that light itself is the field in flight. And then we followed Einstein one level further down. The electric and magnetic fields are not two things but one thing, and the way it splits depends on who is watching. Magnetism, for currents in wires, is electricity as seen from a moving seat, a relativistic bookkeeping correction, magnified into workshop strength force by the enormity of charge. That is the tower as it stood at the dawn of the 20th century. It explains the compass, the motor, the generator, the telegraph, light itself. It is one of the most successful structures of thought our species has ever assembled, and it contains a hole, in what should be the easiest place of all, the refrigerator magnet. The wire's magnetism came from current, charges visibly driven by a battery. The lodestone has no battery. Nothing is being pushed through it. It sits inert on a shelf for a century and loses nothing. Where is its current? Ampere, you will remember, had guessed the answer back in 1820. Perhaps matter itself contains tiny circulating currents, microscopic loops of moving charge, whirling in eternal alignment. By the early 20th century, that guess looked better than ever, because the atom had finally acquired an internal picture: electrons, discovered in 1897, apparently orbiting a dense nucleus like planets around a sun. Every orbiting electron is a tiny loop of current. A tiny loop of current is a tiny magnet. Line up enough of them, and there is your lodestone, magnetism explained, from the bottom up, with nothing but classical physics. It was a beautiful theory, and in 1911, a doctoral student in Copenhagen proved it could not possibly work. His name was Niels Bohr, the same Bohr who would shortly become a founding father of quantum theory, and buried in his dissertation was a calculation of what classical physics genuinely predicts for the magnetism of matter, not what it suggests, what it strictly requires. Take any collection of charged particles you like, electrons, ions, as many as you want, arranged however you want, and let them move under classical mechanics and electromagnetism, in thermal equilibrium at any temperature. Ask for the total, net magnetization of the collection. The classical laws grind through the statistics and return one answer, always, with no exceptions and no loopholes: zero. Exactly zero. Every circulating current that produces magnetism one way is precisely offset, in the statistical ledger of classical physics by motions producing the opposite. The orbits that were supposed to be Ampere's little loops cancel out, completely, mathematically, unavoidably. 8 years later, in 1919, a Dutch doctoral student named Hendrika Johanna van Leuven, one of the first women in the Netherlands to earn a physics doctorate, proved the same result independently and in greater generality, and the theorem now carries both their names. The Bohr-van Leuven theorem. In classical physics, matter cannot be magnetized. At all. Ever. Do not let the dry name slide past you. Hold the refrigerator magnet in your mind and hear what the theorem is actually saying. This object cannot exist. The magnetization of iron is not merely unexplained by classical physics. It is forbidden by classical physics, with the full force of a mathematical proof. The 19th century's complete and glorious edifice, Maxwell's equations, Newton's mechanics, the statistical theory of heat, everything we have celebrated for the last hour, when aimed at the single oldest object in our story, the lodestone that started it all in the hills of Magnesia, returns a flat impossibility. The stone in the child's hand refutes the physics of Faraday, Maxwell, and Einstein's wire, all by itself, just by clinging to a nail. There is something almost comical in the timing. Physics had explained light, unified space and time, and traced the compass to relativistic bookkeeping, and it could not account for the magnet on the door of the icebox. And notice that the theorem also quietly murders the explanation we just celebrated one part ago. The relativistic story, magnetism as frame-shifted electricity, is airtight for wires, where a battery drives the current, but the permanent magnet was supposed to get its current from orbiting electrons, and the theorem says thermal equilibrium washes every classical orbit's magnetism away to nothing. If classical charges in classical motion cannot magnetize matter, then whatever is circulating inside the lodestone is not moving classically. The eternal, sourceless, unstoppable something inside a permanent magnet obeys different laws of motion from every planet, cannonball, and wire. The 19th century ever measured. The theorem's reach deserves one more turn of the screw, because it does not only forbid the lodestone, matter responds to magnetic fields in weaker ways too. Some materials are paramagnetic. Brought near a magnet, they are faintly attracted, their internal magnetism leaning toward the field. Others are diamagnetic, faintly repelled, leaning away. Water is diamagnetic, so is human tissue, which is why, in a famous 1997 demonstration in a Dutch laboratory, a living frog was floated in mid-air on the diamagnetic repulsion of a 16 Tesla field, unharmed and visibly bewildered. The Bohr-van Leuven theorem forbids all of it. The leaning toward, the leaning away, the floating frog, every whisper of magnetic response in every material, not just the strong grip of iron. Classically, matter must be perfectly, universally indifferent to magnetic fields. The real world's answer runs from the faint repulsion of a frog to a stone that lifts nails, and every point on that spectrum is a quantum phenomenon. There is no such thing, anywhere in existence, as classical magnetism in matter. Physics stood at this cliff edge for roughly 2 decades, and it is worth appreciating how the impossibility was finally read. A lesser generation might have treated the theorem as a technicality to be patched. The generation of 1900 to 1930 read it correctly, as a message that the entire classical picture of matter was wrong at the root. The same years were piling up other impossibilities. Glowing objects radiating colors classical physics could not predict. Atoms refusing to collapse when classical electromagnetism demanded they must. Light behaving as particles in one experiment, and waves in the next. The magnet's impossibility belongs to that family. Each one was a place where the smooth, continuous, clockwork universe of classical physics gave an answer that reality flatly contradicted. The resolution, when it came, was not a patch. It was quantum mechanics, a new mechanics for the small, in which energy comes in steps, motion comes in discrete states, and matter at the bottom simply does not behave like tiny cannonballs. So the question tonight sharpens once more, and becomes the question of the next part of our journey. If the magnetism of a permanent magnet cannot come from classical motion, if every ordinary orbit cancels to zero, then what is left? What is circulating inside the lodestone, holding its grip for centuries without a battery, immune to the theorem that kills every classical explanation? The answer, discovered in a laboratory in Frankfurt in 1922 by two physicists firing silver atoms through a lopsided magnetic field, turned out to be a property of matter that nobody had imagined, a form of rotation belonging to particles that are not rotating, a compass needle built into the electron itself, deeper than motion, deeper than orbits, woven into what an electron is. The universe, it turns out, hides a magnet inside every single electron in your body. And the story of how we found it begins with a beam of silver splitting cleanly in two. Part 8. Spin. Magnetism without motion. In February of 1922, in Frankfurt, Germany, two physicists were running an experiment that, by the account of nearly everyone involved, should not have produced anything interesting. Otto Stern was the theorist and instigator, a stubborn, cigar-smoking master of molecular beams. Walther Gerlach was the experimentalist with the hands to make it work. Their apparatus was almost absurdly simple to describe. An oven that boiled silver, a hole that let a thin beam of silver atoms fly out through a vacuum, a magnet with deliberately lopsided poles that made the magnetic field much stronger near one pole than the other, and a glass plate to catch the atoms at the far end. If a silver atom carries a little internal magnet, an uneven field will tug it, up if the atom's magnet leans one way, down if it leans the other, hard or gently depending on the angle. Classical physics made a clean prediction. The atoms tumble out of an oven. Their internal magnets should point every direction at random, like dropped needles. The beam should smear into one continuous vertical band on the glass, every deflection from maximum up to maximum down, all represented. The beam did not smear, it split. On the glass plate, after hours of accumulation, there developed two crisp, separate lines. Atoms deflected fully up, atoms deflected fully down, and nothing in between. Not a spectrum of orientations. 2. As if every needle dropped on a floor landed pointing exactly north or exactly south, and no needle anywhere landed at an angle. The silver atom's internal compasses were not allowed to lean. Nature, at the bottom, permits certain quantities only certain discrete values, and the Frankfurt glass plate was among the first times a human eye saw that rule written directly in silver. When Gerlach developed the plate and saw the doubling, he sent Stern a triumphant postcard bearing a photograph of the split beam. The result electrified European physics, though its full meaning took years to decode. What the beam was revealing had a name coming: spin. Here is what spin turned out to be, and I will be honest with you about how strange it is, because the strangeness is the point of our whole night. Every electron behaves, in every experiment ever performed, as if it were a tiny spinning ball of charge, and a spinning ball of charge is a loop current, and a loop current is a magnet. The electron acts magnetic, permanently, unstoppably. But the electron cannot actually be a spinning ball. Follow the classical picture for one step, and it detonates. To generate the measured magnetism, a ball of the electron's measured size would need its surface moving faster than the speed of light, not slightly faster, wildly, impossibly faster. And as far as every measurement can determine, the electron has no size at all to spin with. It behaves as a true point, with no measurable diameter down to the smallest scales ever probed. What the electron has is the output of rotation with no rotation underneath. A fixed, built-in quantity of angular momentum and a fixed, built-in magnetic moment. Physics kept the word spin as a label, and I want you to hear it tonight, the way physicists privately hold it. Not as a description, but as a white flag. The electron is a magnet the way it is a charge, intrinsically, as part of what it is, with no mechanism inside, no moving parts, and no picture that survives inspection. The oldest mystery in this story, the lodestone's sourceless, batteryless, eternal grip, reappears at the bottom of the universe, attached to every single electron, and this time there is nothing underneath it to point to. In 1928, Paul Dirac, we will meet him again shortly, wrote down the equation that merged quantum mechanics with special relativity, and something remarkable fell out of the mathematics unbidden: spin. The equation demanded that the electron carry exactly the angular momentum and the doubled magnetic effectiveness that experiments had measured, not as an added assumption, but as a consequence of making quantum theory respect Einstein. The two revolutions of our night, the relativity that explained the wire, the quantum theory that the magnet demanded, locked together at the electron, and their joint signature is its magnetism. That signature has since become the most exactly verified number in all of science. The electron's magnetic strength, measured with a single electron held for months in an electromagnetic trap, agrees with the theoretical prediction of quantum electrodynamics to roughly 1 part in a trillion, 12 decimal places of agreement between a pencil and paper theory and a trapped particle. Nothing else humans believe, in any field of knowledge, has ever been checked to that precision and survived. And it is a statement about a magnet. Let the precision of that number reach you as a physical fact rather than a statistic. 1 part in a trillion is the precision you would need to measure the distance from your bed to the moon and get it right to within the width of a human hair, and then do 1,000 times better. That is how exactly we can predict the behavior of the magnet inside the electron. And it sits alongside, in the same theory, a complete inability to say what spin is. We possess 12 decimal places of how and 0 decimal places of what. If one sentence captures the strange condition of modern physics, the condition this whole night keeps circling, it is that one. So the refrigerator magnet's secret is spin, but one ingredient is still missing, and it is the strangest of all. Iron atoms have unpaired electron spins. Each iron atom is a small, permanent magnet. But why do trillions of them agree on a direction? Their little magnetic fields tugging on each other cannot be the answer. Calculate that interaction, and it is roughly 1,000 times too weak, easily scrambled by heat at room temperature. The true aligning force, identified by Werner Heisenberg in 1926, is called the exchange interaction, and it is not a magnetic force at all. It is a consequence of the Pauli exclusion principle, the quantum rule that no 2 electrons may occupy the same state. In iron, that rule makes the electric energy of neighboring atoms depend on whether their spins agree. Parallel spins force the electrons apart in space, reducing their electric repulsion. The result is an effective agreement between neighbors, enforced not by magnetism, but by electricity, filtered through quantum bookkeeping, and it is enormously strong, which is why iron holds its alignment at room temperature. The magnet is not held together by magnetism. It is held together by the exclusion principle, a rule with no classical analogue, doing electrostatics. Now descend into the bar of iron and watch the machinery assemble. You are inside a grey crystal city, and every atom around you is a compass needle. In this neighborhood, the exchange interaction has everyone pointing the same way. You are standing in a domain, a district, of perhaps a million atoms, in perfect agreement. But drift toward the district's edge, and you cross a boundary wall a few hundred atoms thick, where the spins twist smoothly around, and beyond it lies another domain, pointing another way entirely. In an ordinary nail, the districts cancel. The city, as a whole, is silent, which is why a nail is not a magnet. Now an external field sweeps through. Someone outside is stroking the nail with a lodestone. The walls themselves begin to move. Districts aligned with the field annex their neighbors, boundaries sliding atom row by atom row, disagreeing regions shrinking, until the city speaks with one voice and the nail has become a magnet. Heat it past 770 degrees Celsius, iron's Curie point, and thermal chaos overwhelms the exchange agreement. The districts dissolve and the magnetism dies, exactly as Gilbert saw 4 centuries ago, without any possibility of knowing why. And with that, the refrigerator magnet stands explained, the deepest explanation our species possesses. It is a quantum object you can hold. Its grip is the summed spin of some 10 to the power of 23 electrons, aligned by the exclusion principle, each electron a magnet with no mechanism inside. It needs no battery, for the same reason a stone needs no battery to keep being a stone. Spin is not a process that runs down, it is a property that simply is. Every one of the 2,000 years of wondering, from Thales to the song navigators to Gilbert, was wondering, without any way to know it, about quantum mechanics. But do not relax yet, because our ledger still carries an unpaid line. Twice tonight, we have brushed against the fact that magnetism, unlike electricity, has no particle of its own, no isolated pole, no magnetic charge, nothing you can hold that is purely north. In 1931, the same Dirac whose equation gave us spin proved something about that absence that has haunted physics ever since. If even one isolated magnetic pole existed anywhere in the universe, it would explain one of the deepest unexplained facts about reality. The search for that particle, and its resounding, decades-long silence, is where we go next. Part 9. The missing half of the field. Every field of physics has its famous absence, the thing theory invites, and nature declines to provide. Magnetism's absence is the purest of them all, and we have been stepping around it all night. It is time to face it directly. Electricity has particles of charge. The electron carries 1 unit of negative charge, alone, unaccompanied. The proton carries 1 unit of positive, equally alone. You can separate them, collect them, spray them across a vacuum one at a time. Positive and negative are divorceable. Magnetism's north and south are not. Cut the magnet, and each half regrows the missing pole. Grind it to atoms, and every atom is still a complete 2-poled magnet. Descend to a single electron, and even that ultimate fragment carries a north and a south welded together in a point. Nowhere, in any rock, any meteorite, any particle collision, any cosmic ray shower ever recorded, has anyone caught a bare north pole by itself. The hypothetical particle that would carry such a lone pole has a name, the magnetic monopole, and its non-appearance is written into the very structure of Maxwell's equations. One of the 4 simply declares that magnetic field lines never begin and never end anywhere. Electric lines are allowed to start on charges and stop on charges. Magnetic lines must close on themselves, loops without ends, forever. That asymmetry between the electric and magnetic halves of one unified field is sitting right in the foundations, unexplained, like a house built with 1 door that opens and 1 painted shut. You might file that under tidy facts rather than mysteries. Nature simply has charges of one kind and not the other, were it not for what Paul Dirac discovered in 1931. Dirac was perhaps the strangest and most austere genius of the quantum generation, a man of legendary silence who trusted mathematical beauty over intuition, and whose equation had already conjured spin and predicted antimatter. In a paper titled Quantized Singularities in the Electromagnetic Field, he asked an innocent question: is the magnetic monopole actually forbidden by quantum mechanics? The expected answer was yes. Quantum theory's treatment of magnetism seemed to have no room for it. Dirac found instead that the monopole fits, provided one condition holds. The product of the fundamental electric charge and the fundamental magnetic charge must equal a fixed combination of nature's constants. And that condition, he noticed, detonates into something extraordinary. If even one magnetic monopole exists, one, anywhere in the observable universe, at any time in its history, then quantum mechanics requires electric charge to be quantized, to come only in exact integer multiples of one fundamental unit. To feel the force of that, you need to know that charge quantization is one of the deepest unexplained facts about reality. Every electron in the universe carries exactly the same charge, to the limits of the most exacting measurement, and the proton, a completely unrelated composite particle built from quarks, carries exactly the opposite charge, matched so perfectly that atoms are neutral to better than 1 part in 10 to the power of 21. Nothing in standard electromagnetism requires this. Charge could have come in any messy assortment of values, and the equations would function. Instead, everything is minted in identical units, as if from a single die. Why? Dirac's theorem offered the only explanation anyone had ever produced. Because somewhere, in some corner of the cosmos, there exists at least one bare magnetic pole. One lonely particle would discipline every charge in the universe. Dirac himself put it with characteristic economy. One would be surprised, he wrote, if nature had made no use of it. The subsequent history took his hint seriously in the most ambitious way possible. In the 1970s, physicists constructed grand unified theories, frameworks in which electromagnetism and the two nuclear forces emerge from a single parent force that reigned in the first instance after the Big Bang. And these theories do not merely permit monopoles. They require them, heavy, stable magnetic charges that must have been minted in the searing first moments of the universe, with masses on the order of 10 to the power of 16 times the protons, a single elementary particle weighing roughly as much as a living bacterium. The early universe should have made them in enormous numbers. They should be everywhere. They are, notoriously, nowhere, and that embarrassment, the monopole problem, became one of the original motivations for the theory of cosmic inflation. If the infant universe underwent a burst of exponential expansion, the primordial monopoles would have been diluted to near zero density, perhaps a handful in our entire observable volume, which leaves the modern search parties in a strange position, hunting a particle whose absence has already reshaped cosmology and whose discovery, even of a single one, would confirm physics beyond the standard model at a stroke. They have looked everywhere. Superconducting loops that would register the passage of a single monopole through them as a permanent, unmistakable jump in current. Ancient minerals and lunar samples, searched for trapped magnetic charge, accumulated over billions of years. The modal experiment at CERN's Large Hadron Collider, a dedicated monopole trap operating since 2015, plates of aluminum waiting to swallow any magnetic charge the collisions produce, probing masses up to several trillion electron volts. Cosmic ray observatories scanning for the distinctive trail a heavy magnetic charge would carve through the atmosphere, decade upon decade of silence, with one exception, and it is one of the strangest single data points in the history of physics. On the night of February 14th, 1982, Valentine's Day, a superconducting monopole detector, built by Blas Cabrera at Stanford University, recorded, at around 2 in the afternoon, with nobody in the room, a single clean jump of precisely the size a passing Dirac monopole would produce. One textbook perfect event. It has never happened again. Not in Cabrera's own enlarged detectors, not in anyone else's, not in more than 40 years of watching. It cannot be verified, cannot be repeated, and cannot quite be explained away. Physicists remember it the way sailors remember a light seen once at sea. On the anniversary, colleagues have been known to send Cabrera wry Valentine's greetings. The event sits in the record, an unrepeatable maybe, the closest humanity has ever come to holding the missing half of the field. A caution belongs here, because you may have seen headlines announcing that monopoles have been found. In a sense they have, and the sense matters. In certain exotic crystals called spin ices, the collective behavior of thousands of atomic spins can organize itself into excitations that move through the crystal and behave, mathematically, like separated north and south poles wandering apart. They are real, they are measurable, and they are beautiful physics. They are also not the particle Dirac described. They exist only inside their host material, the way a wave exists only in water. Extract one into empty space, and there is nothing to extract. They are impersonations of the monopole staged by ordinary matter, proof that nature enjoys the mathematics of magnetic charge, and no evidence at all that she ever minted the coin itself. The fundamental monopole, the one that would complete Maxwell's equations and explain the quantization of charge, remains unseen. If it were found, the four equations would snap into a perfect symmetry, the electric and magnetic halves finally mirror images, the painted door swinging open at last. And part of the quiet suspicion among physicists is precisely that the symmetry is too beautiful for nature to have declined. So the ledger on the monopole stands as follows. Theory says its existence would explain a founding fact of reality. Grand unification says the early universe should have made them. Cosmology has already been rebuilt, partly to explain why we see none. And every search has returned empty, one ambiguous Valentine's night aside. Notice what this does to our night's question. Magnetism is the only fundamental phenomenon we know that appears to exist entirely without its own substance. Every magnetic field in the universe, every one, from the fridge door to the largest structures we will meet in the next part, is generated at second hand, by electric charge in motion, or by the intrinsic spin of particles that carry electric charge. Magnetism has no carrier of its own, no native particle, no independent existence. It is, everywhere and always, something electricity does. Unless, of course, one Valentine's Day signal was real. And with the missing particle duly mourned, we can finally lift our eyes, because it is time to ask how big this story gets. We have explained the magnet in your hand. We have not yet looked at the magnet you are lying on, the one 8,000 miles wide, with a core of molten iron, whose field is at this moment deflecting a storm of particles from a star, and beyond it, the one the size of a galaxy. Part 10. A Magnetized Universe. Underneath your bed, 4 notches down the ladder of the world, through the floor, the bedrock, the churning mantle, there is an ocean of liquid metal, and it is running the oldest machine on Earth. The outer core is a shell of molten iron alloy, roughly 2,200 kilometers thick, hotter than the surface of the sun, circulating in slow currents, driven by the planet's inner heat and its rotation, flows of liquid iron, moving at speeds of millimeters per second, about as fast as your fingernails grow. Molten iron is a conductor, and Faraday taught us what conductors moving through magnetic fields do. They generate current, and currents generate magnetism. In the core, the loop closes on itself. The moving metal generates fields, the fields thread back through the moving metal, and the whole engine sustains its own magnetism, a self-exciting dynamo, converting the planet's interior heat into the field that swings every compass needle on the surface. Gilbert was right that the Earth is a magnet. The 20th century discovered it is not a magnet like a lodestone, a frozen block of aligned spins, but a magnet like a process, a flame rather than a stone, continually regenerated and never still. That is why magnetic north wanders. In recent decades, it has sprinted from the Canadian Arctic towards Siberia, at up to 55 kilometers per year, fast enough that the official world magnetic model used by navigation systems required an emergency update in 2019. And it is why, written in the frozen magnetism of seafloor rocks, we find the field's most unsettling habit. It reverses. Hundreds of times in the geological record, north and south have traded places. Most recently, about 780,000 years ago, the dynamo faltering, scrambling, and relighting the other way up. The warning signs Gilbert's era logged and ignored, the creeping declination, were the surface flickers of a living engine. And that engine is not decoration. The field it maintains inflates a protective cavity around this planet, the magnetosphere, that deflects the solar wind, the perpetual storm of charged particles our star throws off at hundreds of kilometers per second. Stand under an aurora and you are watching the deflection system operate. Charged particles funneled along the field lines toward the poles, lighting the upper air like a fluorescent tube. Mars, our nearest lesson, ran a dynamo once, and lost it billions of years ago, as its smaller core cooled. The solar wind then stripped away most of the Martian atmosphere, over the eons, molecule by molecule. The desert we photograph today is, in part, what a planet looks like after its magnetism dies. Climb the ladder outward, and the story repeats at every landing, always larger. The sun is a dynamo of plasma rather than iron, and a far more violent one. Its churning interior winds its field into knots that burst through the surface as sunspot pairs, regions where the field concentrates thousands of times over, and snap into flares and eruptions that fling billions of tons of magnetized plasma across the solar system. The entire solar magnetic engine turns over on a clock. Roughly every 11 years, the sun's global field reverses polarity, north for south, a full-body magnetic flip that has been tracked without interruption since the counting of sunspots began centuries ago. Jupiter's dynamo, running on metallic hydrogen, inflates a magnetosphere so large that if your eyes could see it, it would loom in the night sky wider than the full moon. One of the largest coherent structures in the solar system, invisible only because it happens to be made of field. The ladder has higher rungs still, and the view from the top is worth one look. When a giant star dies and its core collapses into a neutron star, a ball of nuclear matter 20 kilometers across, its magnetic field collapses with it, concentrated a billionfold. An ordinary neutron star's surface field runs around 10 to the power of 12 Gauss, and a rare few, the magnetars, reach 10 to the power of 14 to 10 to the power of 15 Gauss, the strongest magnetic fields known to exist anywhere. At those strengths, the field stops being a background and becomes the main event. Its energy density exceeds the energy equivalent of solid lead. Atoms caught in it are stretched into needles, and the vacuum of space itself is predicted to turn birefringent, splitting and polarizing light, as if empty space were a crystal. A magnetar is what the modest force on your refrigerator door looks like when the universe removes every limit. Same field, same physics. 20 orders of magnitude up the dial. Between the stars, we have even touched the field directly. When the two Voyager probes crossed the boundary of the Sun's magnetic bubble, Voyager 1 in 2012, Voyager 2 in 2018, their instruments, still faithfully reporting after 4 decades of flight, measured the interstellar magnetic field itself, about half a nanotesla, draped along the boundary of our star's domain. 2 machines built by human hands have left the Sun's magnetism and entered the galaxies, and they could feel the difference. Now step off the ladder entirely, out into the space between the stars, because here is where the story stops being about objects and becomes about the universe itself. The gas and dust that fill our galaxy are threaded by a magnetic field, weak by kitchen standards, a few microgauss, about 100,000th of the field at Earth's surface, but present everywhere, and organized. Mapped across the sky, The galactic field roughly follows the spiral arms, an ordered pattern of field lines winding through the disk of the Milky Way from end to end. 100,000 light-years of coherent magnetic architecture. We can see it, though not with visible light. Electrons spiraling along the field lines at near light speed broadcast synchrotron radio emission, and polarized radio waves crossing magnetized gas have their polarization rotated in proportion to the field along the way. Faraday rotation, the very effect Faraday discovered in 1845 when he twisted light with a magnet, now repurposed as the surveyor's instrument of cosmic magnetism. Radio astronomy of this kind is, in the most literal sense available to science, photography of the field. Faraday's iron filing patterns, redrawn at the scale of the galaxy. And what the surveys show is that our galaxy is not unusual. Spiral galaxies generally carry ordered fields of 5 to 15 microgauss, wound through their arms. Galaxy clusters, congregations of thousands of galaxies, the largest bound structures in existence, are magnetized through and through, microgauss fields spanning millions of light-years of thin, searing plasma. Everywhere astronomers have devised a way to look, on every scale, from planets to the largest assemblies of matter in the universe, the answer has come back the same: magnetized. The energy budget makes the point sharper. In the interstellar medium of our galaxy, the energy stored in the magnetic field is roughly equal to the energy of the cosmic rays sleeting through it, and roughly equal again to the energy of the turbulent motion of the gas itself, a three-way equipartition that no one fully knows how to explain. The field is not a trace contaminant of the galaxy. It is a co-equal partner in its energy economy, shaping how gas clouds collapse into stars, how cosmic rays travel, how the spiral arms hold their form. Remove magnetism from the universe, and you do not get the same universe minus some decoration. Star formation changes, galactic structure changes, the story of matter changes. And then, in 2010, came the measurement that pushed the field into the last place it had any right to be. Between the clusters and filaments of the cosmic web lie the voids, regions tens of millions of light-years across, containing almost nothing, no galaxies, next to no gas, the emptiest volumes in existence. Nobody expected magnetism there. Every field we have met tonight was made by matter, and the voids are defined by matter's absence. The test used the universe's own particle beams, certain distant galaxies, blazars, fire jets of gamma rays, across billions of light-years, straight through the voids, toward Earth. When the highest energy gamma rays collide with the faint background light that fills space, they convert into pairs of electrons and positrons, which should then generate a secondary glow of lower energy gamma rays traveling the same direction, a halo the Fermi Space Telescope was built to see. For source after source, the secondary glow is missing. And the cleanest explanation is as simple as it is enormous: a magnetic field in the void, deflecting the charged pairs off the line of flight, smearing their glow away from our view. From the missing light, a flaw on the field's strength. Recent analyses of 22 blazars place it at no less than about 2 times 10 to the power of -17 Gauss. That is an almost comically feeble field, roughly a billion times weaker than the one holding your grocery list to the refrigerator. But it is not zero, and it is in the one place the universe should be magnetically blank. The emptiest rooms in existence are not empty, which raises a question that sounds innocent and is not. Who magnetized them? Every field we have met tonight had a maker, a core, a star, a galaxy. The voids have none. To answer for them, we have to ask where any of it came from in the first place. And that question, you are about to see, has no answer at the bottom. It is the open wound of this entire subject. Part 11. The Seed Problem. Every explanation of cosmic magnetism we gave in the last part shares a hidden flaw, and once you see it, you cannot unsee it. Go back through the list. Earth's field, generated by the dynamo in the molten core. The Sun's field, generated by the dynamo in its churning plasma. The galaxy's field, maintained by a dynamo action in the rotating, turbulent interstellar gas. Dynamo, dynamo, dynamo. And what is a dynamo, precisely? Go back to Faraday's iron ring. A dynamo is a machine that takes an existing magnetic field and mechanical motion, and uses the motion to stretch, twist, fold, and reinforce that field, converting the energy of motion into the energy of magnetism. Read the definition again, slowly, and notice the word that breaks everything: existing. A dynamo amplifies a magnetic field. It does not create one. Run the equations of magnetohydrodynamics, the physics of conducting fluids, with a starting field of exactly zero, and they return zero, forever. Motion alone, however violent, however enormous, makes no magnetism from nothing. The most sophisticated dynamo in the universe, fed a perfectly unmagnetized fluid, produces a perfectly unmagnetized fluid, which means every magnetic field in the universe is an heirloom. The Earth's field is amplified from an older, weaker field that threaded the material of the young Earth. That field descends from the field of the solar nebula, the cloud of gas and dust that collapsed into our solar system. The nebula inherited its field from the interstellar medium of the galaxy, whose field is amplified from the field of the gas that assembled the galaxy in the first billion years after the Big Bang. Each generation amplified what it received, none created what it holds. Trace any field you like, backward through its ancestry, the one in the fridge magnet, the one around this planet, the one wound through the Milky Way's arms, and the genealogy marches back through 13 billion years and more, arriving always at the same question. Where did the first one come from? Physics calls it the seed field problem, and here is its status in one sentence: it is unsolved. Not unsolved as in messy, with competing camps quibbling over details. Unsolved as in the origin of magnetism in the universe is not known. Pointing, once again, is not understanding. And modern cosmology's magnificent maps of cosmic fields are, at the question of origin, exactly where the medieval navigators stood with their needles, in possession of the phenomenon, in ignorance of its source. There are two families of proposed answers, and the fight between them is one of the quietest important arguments in science. The first family is astrophysical. The seeds were made late, by the first structures themselves. Even with zero field, there is one loophole in the no creation rule, a subtle effect called the Biermann battery, in which pressure and density in a hot ionized gas fall out of alignment, driving a feeble trickle of current and breathing a whisper of field into existence. It works in shock fronts around forming galaxies and in the blast waves of the first stars. But the whisper is faint, almost beyond expression, on the order of 10 to the power of -19 Gauss, 100 billion times weaker than the field of the Earth. To dress the galaxies in their observed microgauss clothing, dynamos would have to amplify that whisper by more than a dozen orders of magnitude in the time available, plausible in the disks of galaxies, where rotation winds the field tirelessly, though the accounting is tight. Where the astrophysical story strains is the voids. Galaxies can blow magnetized exhaust into their surroundings, winds, jets from their central black holes, but the voids are, by definition, the places galaxies are not, tens of millions of light-years from the nearest polluter. Getting measurable field into the emptiest rooms of the universe by pollution alone requires the pollution to travel absurdly far and survive absurdly well. The Blazar measurement that closed our last part sits in this argument like a splinter. The second family answers the voids effortlessly at the price of invoking the beginning of time. Perhaps the seeds are primordial, forged not by stars or galaxies but by the infant universe itself, in its first second, during cosmic inflation, when quantum fluctuations were stretched to cosmic size and could, in some models, have included fluctuations of the electromagnetic field, or in the violent phase transitions that followed, at 10 to the power of minus 11 seconds, when the electroweak force split, or at 10 microseconds, when quarks bound into protons. A field born then would have been born everywhere, woven into the fabric before matter had gathered into structures at all, threading voids and clusters alike, because it predates the difference between them. If this is the truth, then the faint magnetism of the voids is the oldest artifact in existence, a relic not of the first stars, nor the first atoms, but of the first second, older than the cosmic microwave background by 380,000 years, a signal from an epoch no telescope can see, surviving in the emptiest places precisely because nothing there has happened since to erase it. Reach for the scale of that idea. We may already have detected, in the missing glow of blazar beams, a fossil of the universe's first moments, and we are not yet sure. The argument, remarkably, is not stuck in philosophy. It has numbers on both ends, closing like pincers. From below, the blazar observations demand at least about 2 times 10 to the power of minus 17 Gauss threading the voids. From above, the Planck satellite's exquisite maps of the cosmic microwave background show no distortion from primordial magnetism, capping any such field at a few nanogauss, a few times 10 to the power of minus 9 Gauss, on cosmological scales. Between the floor and the ceiling stretch about 8 orders of magnitude, the window in which the primordial hypothesis must live, if it lives at all. Every improvement in gamma-ray astronomy raises the floor. Every improvement in cosmological data lowers the ceiling. And a purpose-built instrument is coming for the middle, the square-kilometer array, the largest radio telescope ever constructed, is designed to measure Faraday rotation toward tens of millions of extragalactic sources, a census of cosmic magnetism thousands of times denser than anything existing, capable of mapping the field structure of the cosmic web itself. The seed question, unanswered for a century, is entering the decade in which it may finally be cornered. The primordial camp carries its own scars, in fairness. Models that generate fields during inflation tend to trip over their own assumptions, make the field strong enough to matter today, and the theory generating it typically breaks the rules it depends on, a snag known in the trade as the strong coupling problem, unresolved after 3 decades of attempts. Nature is not obligated to have chosen either family cleanly. The answer could be a blend, late pollution, layered over an ancient whisper. Meanwhile, the fields themselves, whatever their origin, have become an obstacle other sciences must fight through. The observatories that catch ultra-high energy cosmic rays, charged particles arriving with the energy of a thrown baseball packed into a single atomic nucleus, cannot trace them home, because every magnetic field between source and Earth has bent their paths. The galaxy's own heirloom field scrambles the return addresses. Astronomy's newest frontier peers at the universe through a magnetized fog, and cannot chart the fog whose origin it cannot explain. The problem compounds itself. Be honest with yourself about where tonight's journey has arrived, because this is the summit of the strangeness. We began with a toy, and the toy's deepest question turned out to be attached to the first second of time. If the primordial answer is right, then when you feel 2 magnets push apart, the field between your hands and the field in the voids are leaves of one family tree, and the tree is rooted before the first star, the push against your fingers, a great-grandchild of the Big Bang. And if the astrophysical answer is right, the universe found a way to magnetize itself from exactly nothing through a loophole a German astronomer identified in 1950, and the voids will need some subtler explanation still. Either way, the plain admission stands, and I want you to hear it as clearly as anything said tonight. Physics does not know where the universe's magnetism came from. The force in the child's hand has an unexplained ancestor, and the ancestor is hiding somewhere in the first chapters of the cosmos. One task remains for us now. It is time to gather every layer of this long night: the field, the frames, the spin, the missing pole, the unexplained seed, and finally answer, as completely as our species currently can, the question we started with: what is magnetism, really? Part 12. What magnetism really is. At the beginning of tonight, I made you a promise. I said that if you carried the child's question all the way, what is actually happening in the gap between two magnets, I would give you, at the end, the real answer, the deepest one physics currently has, in plain language, with nothing tucked out of sight. You have earned it. Here it is, assembled layer by layer, exactly as we uncovered it. When you push two magnets together, the gap between them is not empty. It is filled with a field, a physical condition of space itself, carrying energy you can measure and momentum you can measure, as real as the magnets and in some ways more real, since the field can leave its sources behind and travel across the universe forever as light. That is Faraday's and Maxwell's layer of the answer. But the field in that gap is not fundamentally magnetic, because nothing is. Electric and magnetic fields are two projections of a single electromagnetic field, and the way it divides depends on the motion of whoever is measuring. The universe does not come with labels reading this part electric, this part magnetic. The labels were ours all along. Nature keeps one field, and your state of motion decides how you slice it. Magnetism is the portion of the electromagnetic force that appears when charge moves relative to you. Electricity, corrected by relativity, wearing a mask 2,000 years older than the face beneath it. That is Einstein's layer. Beneath it lies the quantum flaw. The reason a lump of iron can hold a field with no current and no battery is that every electron is itself a magnet, carrying spin, a form of angular momentum with no rotation beneath it and no mechanism inside it. And in a few special materials, a quantum rule about electrons refusing to share states forces trillions of those spins into agreement. A permanent magnet is quantum mechanics grown large enough to hold. That is the layer Bohr's impossible theorem demanded, and Stern and Gerlach's split beam revealed, and beneath even that, two locked doors. Magnetism has no particle of its own. No isolated pole has ever been found, though a single one anywhere would explain why electric charge comes in exact units. And magnetism has no known origin. Every field in the cosmos is an amplified inheritance from an earlier field, back through 13 billion years, to a first seed that physics cannot yet name, and that may have been written into the universe in its first second. That is the complete answer, as our species currently holds it. Now notice the shape of the thing you are holding. Every layer is solid, tested, measured. In the case of the electron's magnetism, verified to 1 part in a trillion, the most exact agreement between idea and reality ever achieved. And every layer ends in an honest opening. The field is defined by what it does, never by what it is. Spin is a name for a property with no picture underneath. The monopole is a 50-year silence with one unrepeatable Valentine's night in it. The seed is a blank page at the start of the cosmic ledger. This is what understanding looks like at the frontier, not a wall of ignorance, and not a finished cathedral, a structure of magnificent precision whose foundations rest on questions. We can compute magnetism to 12 decimal places. We cannot yet say what it is, in the way the child's question wants. Both of those statements are true at once, and the space between them is where physics lives. And the strangest force turns out to be the least avoidable. Tonight's journey visited the universe's extremes, but the physics never left your room. It is holding you together right now. Reach out, wherever you are lying, and press one finger against something solid. That resistance, the plain fact that your finger does not sink through the table, that the floor holds the bed, that your own body does not fall through itself, is the electromagnetic force between the outer electrons of your atoms and theirs. Nothing is touching anything. Nothing has ever touched anything. Every surface you have ever felt, every hand you have ever held, every kiss, every raindrop on skin, all of it was fields meeting fields, across gaps no eye could see, the same invisible architecture you felt between the toy magnets, running the whole world so smoothly that it took our species 20 centuries to notice the one place, a strange dark stone from Magnesia, where the machinery showed. The magnets were never the exception. The magnets were the one honest view of the rule our species was ever offered. There is life in this story too, quietly. Every autumn, European robins small enough to sit in your palm navigate thousands of kilometers, using, by the best current evidence, a quantum chemical compass in their eyes. Molecules whose reactions tilt with the Earth's field, possibly letting the bird perceive magnetism as something overlaid on vision. Sea turtles read the planet's field to find the beach where they hatched. Whatever it is like to be a robin in October, it may include seeing the great heirloom field of the Earth, the same field that shielded every ancestor you have ever had from the solar wind, patiently, for 4 billion years, while its poles wandered and flipped hundreds of times, and no generation of living things ever noticed the guardian at work. And where understanding arrived, it repaid the centuries of wondering with interest. The same spin that puzzled Frankfurt in 1922 now images the interior of your body. A hospital MRI machine is a superconducting magnet, its current circling a closed loop without resistance, needing no battery, a hand-built imitation of the permanent magnet's eternal currents, gently persuading the spins of the hydrogen in your tissues to speak, so that medicine can see a tumor without a single cut. Mesmer's magnetic quackery was debunked by Benjamin Franklin's commission in 1784. 2.5 centuries later, real magnetism diagnoses real disease, and the truth ended up more healing than the fraud. Even the search for the universe's missing matter has become, in the end, a story about magnets. The halls of several dark matter experiments are dominated by enormous superconducting coils, multi-Tesla fields wrapped around resonant cavities, chilled near absolute zero, listening for one predicted whisper. If the dark matter is made of ultralight particles called axions, then inside a strong magnetic field, an axion drifting through can transform into a single faint microwave photon. The detectors are, in essence, radios tuned inside magnets, waiting for the dark to speak. Whether or not the axion exists, the method says something about where physics has arrived. When we want to interrogate the invisible 85% of the matter in the universe, the instrument we reach for is the force from the stone of Magnesia. The lodestone began as a curiosity, became a compass, became a generator, became a hospital scanner, and is now the microphone we hold up to the darkness between the galaxies. And spare one last thought for the machinery that has been running under this entire night. Every fact you have heard arrived at your ears through an unbroken chain of magnetism. Read from storage that records data as flipped magnetic domains, Faraday's districts of iron, shrunk to nanometers and put to work holding civilization's memory, transmitted as Maxwell's waves, amplified by relays and coils, converted to sound by a magnet and a coil vibrating a membrane, powered by generators that are Faraday's 1831 iron ring, scaled to the size of buildings. The 2,000-year mystery did not wait to be solved before going to work. It carries the modern world on its back. The grid, the archives, the airwaves, the voice in your ears right now. A force we barely understand, faithfully holding up everything, every second, everywhere at once. So let the question rest where the evidence leaves it. Magnetism, the strangest force we barely understand, and understand better than almost anything else we know. Both halves of that sentence are true, and tonight you have seen exactly why. It is one face of one field, sliced by motion, flawed by spin, missing its particle, carrying an inheritance nobody can trace to its source. Somewhere out in the dark right now, a gamma-ray beam 8 billion years old is crossing a void, bending almost imperceptibly in a field that may remember the first second of time. While on your refrigerator door, a few centimeters from your breakfast, the same force holds a child's drawing against gravity, and has never once asked for anything in return, and never will. 2,000 years ago, someone picked up a stone that behaved wrongly, and wondered. The wondering built the modern world, and it is not finished. The next time you hold a magnet, tomorrow maybe, let it push against your hand once more. Feel the old question wake, and notice, nothing is touching anything. It never was. Sleep well tonight. The lines of force are all around you, patient and quiet, closed loops without beginning or end. The field will hold.